pleasure to introduce or reintroduce Martin Stringer, who was here a couple of years ago, working with Eve's group, and has since been working in the School of Astronomy, or teaching astronomy, and is working in the School of Physics, although currently on paternity leave. And today he's going to talk to us about the energy crisis.
Thanks very much for inviting me back. I was just going through some of the slides that I gave last time I gave a talk here, and so there's a whole seminar in itself just been going on in the background. I might briefly say that this is kind of what I did before I joined this department, which was work on these computer models. What's happening here is that essentially a bunch of protons and some electrons are falling together under gravity on absolutely enormous scales to form all the structure that you saw in the movies that were playing in the background just now. So this obviously involves a huge amount of computation, and it's really revolutionized the entire field just in the time that I was working in it. So when I started at college, which I'll talk about very briefly in a second, this would not have been possible. And just because of the growth in computer power and the growth in people's knowledge of how to use it. So the scale of this is about the scale of those movies you were seeing. So this is a cluster of galaxies in the middle that's just formed in this computer. If I had to sort of put my finger on my specialism, I suppose it's a little bit smaller scale. So this is a higher resolution simulation of the formation of one of those blobs. And this is how I ended the seminar a few years ago when I last spoke here, when I in fact knew almost nothing about ecology at that point, as opposed to now when I know a little bit more than almost nothing. So the reason I like this is that this is a reasonably good illustration of our best guess of how our galaxy formed. And all of this is just putting protons together and eventually making a few neutrons, which gives you a tiny energy gain. And this basically powers the universe. This powers stars and produces explosions and stabilizes this system. And stabilize is a key word because all the mathematics that goes into why this thing is now stable, spinning around, is the same mathematics that makes ecosystems stable. Now, both the models are often wrong, but in as much as they are ever right, they're very similar techniques that are used. I also like this because this spinning is happening really fast inside when you eventually look at it. And it's very dizzying again and again and again, this system's spinning around. But each of these spins for planet Earth is a different era. So you spin once, you get dinosaurs. Spin around again, you get mammals. Spin around again, who knows? I guess the who knows is what the rest of the talk about. So this was the title I gave last time, which was just to introduce all my previous work and allude a little bit to what I'd be doing here. Which is of course taken from Douglas Adams' work. And this is a great book. If you've never read it, you probably all have, but for a physicist to come across this was an eye-opener, and yeah, I guess it shaped my career. And it shaped his writings and work, and he later on in his speeches came up with quotes like this, which also certainly resonate with a lot of people. So just to explain how I got into all this, I started out in England and spent all my grad studies in California, which I would thoroughly recommend if anyone is ever thinking of going there. It's pretty awesome. Of course, it used to be better when this guy was in charge. Really good time to be there. So just to zoom in a bit, this is a great place to study all manner of things. Especially, there's a really good point break just up here. So if you fancy spending 3 years sitting on a surfboard gazing at these islands, then I would recommend it as well. Not that that's what I did. I did move in the end to Caltech just to kind of keep myself honest, where it's a little bit harder to get distracted, but the walking in these mountains is very beautiful, what's left of them. So Caltech's a funny place. I worked in an institute run by this guy, crazy old physicist dude. He would, just to contrast with what we see at a big campus university like this, people would typically have one, two PhD students. But the group overall was a similar size to this, but way more professors around, and they would have to incentivize the grad students to talk to each other. So he would buy pizza every week, and he would continue doing it as long as we talked to each other about our research without using a computer. So we had to do it all on the blackboard. So people got quite creative. One week somebody actually talked about the pizza. and explained how the pizza was kind of like the universe. Oddly enough, the conclusion has escaped me. And my flatmate's claim was from NASA, which is just up here, and he claimed he was working on a Mars rover. And this old professor claimed he was writing movies with Hollywood scriptwriters and working on gravitational waves. And you're just thinking, okay, all these people are crazy. Anyway, so I was just quietly doing my work. Little did I know, years later I'd come to UQ, and those very islands that I hadn't just been spending 3 years gazing at on a surfboard would actually be the first project I was assigned to here. And it's all about this little bird, which is still here, but has been extinct here. So the larger of the islands, Santa Cruz, has made some progress recently when they stopped ranching. So you can't see it necessarily clearly first time, but the numbers are quite encouraging. It's had a 50% regrowth of the coverage of oak chaparral. Meanwhile, unfortunately, Santa Rosa has not recovered. And the understanding is that it doesn't have any birds to ecosystem engineer it, which is sad because the potential coverage is really quite substantial. So we can have 6-fold improvement in reforestation here. So, you have to be careful what you ask a physicist to look into. So I tried to build a model that would individually model every single bird in this system and tune it. I was building on work by Chris Baker and a whole group of people in America working on this problem where they put field data into a mathematical model. And I made it an individual model to try and understand the system a bit better. Uncovered a few extra bits and bobs, but it's mainly good for seminars, this, because it allows you to quickly give an idea. So what's happening here is the birds are finding all these extra little patches of potential vegetation and reseeding it. And what we're doing is we're taking the parameters from the island where we know what happened and putting them into the island where we think we could put the bird back and we want to know what might happen. So we're trying to use what we know to recreate what we don't know, which I guess was the theme of all the work I did here. And it's where some skills from physics can be useful, if guided sufficiently well by more knowledgeable ecologists, which I was very lucky to work with. So I did go back from California to Northern England. That move I wouldn't recommend so much, but once you get used to the cold, it's very nice. Went to France, where I met Catch at the back, and to Tenerife, which is worth mentioning, and I might come to in a minute. When I arrived back in Australia, I gate crashed the Astro Group meeting because I had some friends here, and this cake was on the table because they just discovered gravitational waves. And on the plane on the way over, I watched this film, and there is the crazy professor who's credited with the scriptwriter. And he won the Nobel Prize the next year. So, I guess maybe he wasn't so crazy after all. So it's nice to have been working with these people. But I felt that after working on all these amazing objects, which I was fascinated by and I'm still fascinated by, and I love teaching people about them, I now rather understand these things if I can be any help at all. So this is the paper by Alex and Chris and Hawthorne, none of whom are unfortunately here, which was the second paper that I was involved in, and Hugh, who is here. And this is one of the many great photos which helped us publicize this, taken by a friend of Alex, of leopards still just about hanging in there in urban Mumbai. This other helped a little bit with this great paper by Hui, which I'd recommend, and then got involved in this project with Natalie and Matt. Matt took charge of this and led to a really nice, short, to-the-point letter about why all of us just keep flying, as if there's no problem. And we'll come back to that later. Just a quick word about Tenerife, because I just can't resist telling people a little bit about this amazing place. It's an archipelago here. It's where people used to stop on the way to Australia when they sailed there. And this is what it looks like. It's a pretty inspirational place to hang out. It's really hard to keep caring about the other side of the universe when you live somewhere like this. And there's a nice story here that this forest you can see, it's a bit patchy, but pretty good coverage around here. It was almost all gone, and they managed to regrow it. And if you walk through here, as there's sort of pilgrimage that still happen where you sort of walk virtually halfway across the island, then you can see what had happened to it in the places where it hasn't grown back yet. And it's just very sad to think that it could have all gone, and very nice to realize that it is possible to save these things. And also because the landscape up here is pretty awful. It's very beautiful, but it's pretty awful. The idea that the whole island might be a desert. So the observatory's up here, and it gives you this amazing perspective on everything. It's 4,000 meters up there, incredible place. So you're typically above the clouds. And just to have a little bit more astronomy before we move on, if we move further back still, I went to a talk recently by an astronaut, and astronauts always come back campaigning for the planet. It's funny. And this guy, Scott Kelly, said it was just the atmosphere. Just seeing the atmosphere at this angle, you just see how thin it is. And that there's really, we feel very protected, but there's really nothing there. And you feel even less protected if you're here. This is a great, this is I think, the most amazing photo ever taken, which was the first Apollo trip that went to the moon. I actually like it with the lander in. Somehow it gives it that extra dimension, because here's where we live, and this is Plan B, a tin can, freezing cold, with about 3 days worth of oxygen in it. So you know where you'd rather be. The Japanese wonderfully went back to the same spot and took a movie in sort of homage to the original trip, which I like even better. This is I can't imagine what it would be like growing up without these images. So it's just incredible to think that now they're just standard. You click on Google Earth and up it pops. Now, how do we get these images? Well, this one is amazing because when you press play, this was actually taken from the other side of the moon by the Mars explorer on the way to Mars, turned around and just took a shot, just because it was cool. And then it turned around and took another one here where you can see the moon and Earth in the same shot. And then on Mars, so they did build a rover. Should have scrolled around a bit just to get Matt Damon. But if you look back from there, you can see us too, only just there. So we're starting to look less significant. And this is one of my favorite ones from Under the Rings of Saturn from the Cassini Explorer. So that's us, right there. So we're now completely happy with this view of the solar system. And as I said earlier, all of this is being run by slowly turning hydrogen into helium and eventually higher elements. And that's all happening in this thing, which again we rather take for granted. I hope I don't damage the monitor here. The reason I like this photo, this looks like an incredibly stable thing, but these are not parts of the tree. That's sunspots, just picked up by a regular camera taking a photo of this nice guy with his dog. Now if you look at this again in other wavelengths, again I can't resist showing these. This is what it would look like if we could see just in hydrogen emission. So you see that there's just so much activity and structure going on here. If we could see an ultraviolet, it would look like this. And I like this one because Venus has just crept in front here and got itself silhouetted. In X-ray, you'd be able to see into it, just like we can see through us. And this is a great photo because it gives you a sense of scale, because you can put the Earth on here and just start to realize that this may be special to us, this place, but the universe is totally fine either way. So this is just a prelude to talking about solar energy. And I just think all this background is so good. So all of this sun that we have is very impressive, but this is what we teach in the astronomy course, which is about all stars. Our sun's pretty boring. It's kind of in the middle, not very exciting. That's part of the reason we're here. It's very stable, but gives out a lot of energy. It's not quite a Goldilocks star because you can, in theory, have life around any of these. Probably not these guys, because they don't live long enough. But there's a cartoon version of this. Hope everybody knows XKCD. So there's their cartoon version of that chart, which is famous in astronomy. Now what's happening here is up here they're getting brighter, and here they're getting cooler. So hotter is in this direction. Now this is actually a fundamental law of physics that's going on in the background here about how much you radiate based on your temperature. Stars obey this law, and so does everything else. So the nuclear bombs we make on Earth is down here somewhere. Planets are out here. So crucially, our Earth is at 300 degrees, but it also is radiating, as we'll see in a minute. And also we're here, astronomers. I don't know if ecologists would be slightly hotter or cooler. I guess it depends what the topic of. That's right, yes. So they'd be, perhaps a little above the 100 watt estimate here. So all of us sitting here at 300 Kelvin, and we have a much smaller surface area than the Earth, which is the other parameter here. So, but we're all radiating energy at 100 watts. So we somehow need the equation here that this planet's solving in a very fascinating way is it's taking the energy from this thing in the middle and somehow turning it into energy for us. So what we're getting here is about 1.3 kilowatts for every square meter. Have that figure in mind. So we can work out what we've got for the whole planet. Sorry, one click too many. So it's an enormous number, 170,000 terawatts. So tera is 10 to the 12. So at the moment, this is just an inconceivably enormous number, which is as we would want it. An infinite energy supply, maybe. So the trick here is all about the temperature, or the wavelength, so the color of the light, or also photon energy, which I've got on this x-axis for the physicists, so I should change it. Now the energy coming in is at a very different temperature than the energy going out, very different wavelength. And this difference is what makes life possible. Because if we were the same temperature as the sun, you'd have an infinite amount of energy, but there wouldn't be any life here. So you need, it's like the economy. You need somebody to have money and somebody to need it. And basically you can trade off this difference, and that's what life is doing. And the stable temperature is possible because the energy coming in pretty much exactly balances the energy going out. So the plants have worked out roughly where the peak is. It really depends on what axis you plot, anyway. So it's interesting that the plants are choosing to it's more interesting than you might think as to where the plants have decided to operate here as a result of evolution. But they take a pretty tiny fraction. So this is the power that you get at, okay. This is the power that you get at each wavelength, at each color from the light. And this is the theoretical curve up at the top here. It actually depends on the atmosphere, but that's the shape. And the plants get a tiny bit. All of us radiating 10 billion, rounding up to 10 billion, because that's probably going to happen soon, is we are radiating a terawatt. So based on this, it doesn't look like there's a problem. Why is there a crisis? We have this enormous nuclear fireball just pounding energy into the planet. The plants grab a pretty healthy but small chunk of it. The rest just gets re-radiated. And we just want our little bit. What's the big deal? Well, 0.11% of the photosynthesized energy is what we need just to stay alive. Sounds totally doable, except it's about the type of energy. It's an extension of what I was saying about needing to have that temperature difference. Of course, we can only eat certain types of energy. So I got interested in this and started looking up crop yields. And you can get basically 10 to the 7 joules a meter squared for a year. So it's 0.3. So you've got 1.3 kilowatts coming in, and 0.3 is available to eat if you happen to like potatoes. Or I think sweet potatoes get you a little bit more. Probably there's someone in the room who's an expert on this. I'd love to chat to them. So a tiny fraction is really available for us. Now if you just start doing the maths and say, okay, well, is there actually enough land to do this? Well, not really. So if you do the maths, we've basically got a football pitch each. So someone with more artistic skill and also more knowledge of this than me, I sort of feel like you could do a great illustration of each person and their football pitch and what their lifestyle would require. To some extent, the UN is already doing this by giving us all, and the IEA as well, I'll talk about more later, by giving us all sustainable diets, for example. But we don't want to end up in the situation that Matt Damon got himself into, where you're farming potatoes on your football pitch, or if it gets any smaller, you know, your little area just to meet your calorie count. We don't want to get to that type of equation. Now we're okay at the moment, but it's getting awfully close once you start looking at the numbers. And there have been some great seminars on that topic here. So I won't dwell on that anymore. It is possible to power ourselves, but what about our stuff? And this is something I've been taking more interest in, because after doing a postdoc here, I did my second postdoc at the Center for Sustainable Engineering Innovation, which is over in the engineering building. Different world. Amazing. Who knew biologists and engineers were so different? I guess we knew, but it's still amazing to see it really in direct sequence. So how about our stuff? Well, most of us sort of think about electricity as being power consumption, and we'll come back to why that's a bit dangerous later. But if you just look at the Queensland consumption, it's 55 terawatt hours, so that's a terawatt running for an hour over the course of the year. Now if you do a little bit of maths here, it comes down to 1.2 kilowatts. So that's our square meter. If you had a perfect solar panel on a square meter, then you could theoretically power yourself for the year. I've walked out of the camera, haven't I? Sorry. Were you? Sorry. Tell me off if I do that again. So already, it's a really big number. We said we were generating 100 watts, so factor of 10 already, just from electricity, domestic and our share of the industrial electricity usage in our own state. Now if we drive around, you can work out, just share the fuel consumption across the whole population. So it equates to a steady usage of energy of about the same. So what I'm doing is I'm transferring everything as to an average power consumption. Obviously, in reality, it spikes up when you go for a drive and then drops to zero. But if you just average it out, so that we get a handle on what the sustainable power balance could be. Now, this is the big one, which is really tricky to estimate for anybody, or even for a country. It's a whole PhD thesis, as we'll see in a minute. It's use stuff. Because we get used to everything having been manufactured for us. Well, that manufacturing energy is very difficult to trace back down the line. Pretty much, it just equates to money. It's amazing how everything works. And what's really interesting is that if something's cheap, it means it was probably made with coal at the moment. Hopefully that will cease to be true, as I'll explain in a little while. But if something has been something that required a lot of energy to mold it, all of these bits of metal here, then it was made with cheap energy. And possibly cheap labour as well, but that's another seminar, which wouldn't be given by me. And then this is the big one, of course, which we wrote a little paper about, which is about the flying and how we adjust our behaviour to accommodate this. And it's just puts you off the scale. So what would be regarded as quite standard, sort of modest behaviour for a scientist, still is almost as much as all your other energy use put together just for a couple of trips. One big one, one short one, for example. So if you put all this together, then we end up, as an organism, using 100 times the energy that's required to keep us alive. Now, we did the sort of football pitch calculation and established that there was hope. And if we managed the land well, we could actually keep 10 billion fed, hopefully with a more interesting diet than potatoes, and perhaps save some wildlife. But if we start needing that land to produce this energy from photosynthesis, it's game over, as far as I can tell from these numbers, as most people concede, I think. So it's our paper, just showing, by the way, just as a quick aside, these bars were showing the response that conferences have had that we investigated. Any colour means any response at all to the sort of conundrum. So most people are just hoping that it will go away. So I got interested in who's consuming all this. So we came up with 8 kilowatts there, call it 10. That's an Australian. So I just looked up some numbers, we shouldn't spend too long on this plot here, but here's Australia. These are just a list of national averages. But obviously, the consumption, what's going on here is this is direct energy consumption and then who's using it. So you can see most of the people in the world are down here at like 1 less. So almost everybody on the planet is living at a sustainable rate. Now, if you just multiply the x-axis by the y-axis, then what you're getting here is now the same type of plot that we were looking at before with the sun. So now the area under this curve is saying how much energy each share of the population is using. So all these people here who are invisible on this graph, the people like us who are demanding, you know, their 10 kilowatts constantly, stuff, electricity, flying, driving. Suddenly they're using something like half. They're using up half the energy of the world. So this is a standard sort of Pareto situation, where a small fraction are using a large fraction of the resource. So these tiny countries out here with huge energy uses are probably not the ones to look at. It's the Australias and the Canadas and the United States. Now, this is just the start of the story, but I think these two pictures are very important to understand, and there's some great work done by people who are actually experts in the economics. One of whom is Andrew Pascal, who, if you haven't met, I would recommend buying a beer for, because he has amazing experience in this whole industry and has chosen to come and do a PhD here. Now, he made these figures. He made figures about this which are more interesting than the ones I just flashed up, because what they do is they deconvolve what happens in the country with what's happening with people inside the country. So the classic picture here, I need a pen. What this is saying is, to sketch while I'm at it, is if you have quality of life, that's what we want. So the y-axis is what we want. And you think that you can get quality of life for humans by energy. Now, you sure as hell can, because what we start with here is people who have nothing. And then suddenly they can cook food. Hey, woohoo! Now, that sounds like it shouldn't be relevant now, but it's incredibly relevant in his thesis. It says how many people in the world can't do that. And the problem is that actually life's getting a bit better for some of these guys, but the better means that they can now get some fuel, and there's a lot of them. So it's very important for us that we provide clean energy for them to do that before they just grab the first thing that's available, as anyone would in that situation. And then eventually maybe you can turn the lights on. And then maybe you can start to travel a bit. And then basically what happens is there's diminishing returns after that. And we're over here somewhere. Some of us are probably over here off the scale. So the question is, we need to get all of these people, this demands a new color. We need to get these people back to here, and we need to get these people up to here without going past there. And if we're still over here having a great time, hey guys, soon you can be like us, then this is not going to work. So we need to be here shouting from the top of the mountain, this way, this way, this way. And hopefully it'll work, if that is what happens. So there is a little area here where if you do the kinds of maths that I was really just touching the surface on here, and you do it very thoroughly, you can actually see 10 billion people existing with a high quality of life and keeping the planet running. Just perfect. Pretty low energy consumption, best quality of life in the world. Are they really though? So if you change it to, so if you deconvolve it, then the rich people in Norway are not doing so well. But apparently, you know, even the people without too much energy to burn in Norway are still having a good quality of life. But this is production. This is the energy produced in that country. So this is the kind of thing that allows, you know, people running these countries to sleep well at night. Well, they can't really, because when they buy all their stuff, it was all made with coal somewhere else, but it got made because they wanted it. So then the magic sort of Scandinavian dream changes a little bit, and these guys are still pretty good, by the way, but even these guys here, the low consumers in Norway, it's still jumped up because all of their IKEA furniture, all of their gadgets, all of their stuff was still made with coal somewhere in Indonesia or China. So this calculation that Andrew's done to account for people's consumption in the best way possible given the data is really potentially hugely important. So let's suppose we want to do this. Well, it's going to have to be solar. It's the only viable energy source that could work. And what's really good, we want 100 terawatts. So we want all of the world to live like Queenslanders. The area of this on this scale required for that is just this. Now, the IEA wants us to actually get lower than that for reasons we'll explain, and that's a much smaller area still. So they only think that we should use a fifth. So we've got the technology we've got. We've got solar panels that work at about 20%. So if we do the maths there, how much of Australia would you need to cover to actually solar power the entire planet so that we could all live like Queenslanders? Well, Queensland. So, you know, we have to be careful what we offer as the high educated, high demand population. But, you know, that's not such a crazy idea. If you divvied all this up, put some of it in the middle here, now there's going to be a biodiversity and ecology cost wherever